So this will be the fourth lecture out of chapter 15, and this will be the last lecture. So on this lecture, we cover what's known as the Diels Alder reaction. So this is an example, classic example of the Diels Alder reaction. So basically what happens in this reaction, so you have what's called a diene, and it reacts with a dienophile, something that loves dienes. So what happens is we're going to take these two electrons in the pi system, make a bond to that carbon. We're going to take these two electrons and move them there to make a double bond between those two carbons. And we're going to take the other two pi electrons and make a bond between these two carbons. So then you would make that. You would make cyclohexene. So is this a significant reaction in organic chemistry? And the answer is yes, it is, because you make two carbon-carbon bonds and one reaction. So anytime you can make a carbon-carbon bond in organic chemistry, that's a significant reaction. And if you can make two carbon-carbon bonds in one reaction, then that's really a significant reaction. So all you have to have is a diene and a dienophile and simply heat it up, and the reaction works. So we'll go through the mechanism in a little bit. It's a pretty complex mechanism. This would definitely be a lecture to pay very close attention to. This is probably one of the most difficult concepts for students in this class to grasp. The theory is, we'll just look at the theory in the very basic sense, but it's a pretty complex theory. But anyway, the basic mechanism, again, we just take these two electrons there, those two there, and those two there. So we're always making bonds between the ends of the pi system. Okay, so now we have, so we're making that bond, we're breaking that double bond, we're making that double bond, we're breaking that double bond, we're making that bond, and we're breaking that double bond. So we're making and breaking 6 bonds all simultaneously. So that's your transition state, making and breaking 6 bonds all at the same time. And then it goes on to product. So this belongs to a class of reactions called pericyclic reactions, and there's a lot of different types of pericyclic reactions. They're what are called chelotropic reactions. The one that we're looking at is what's called a cycloaddition. There's electrocyclic reactions, ene reactions, sigmatropic rearrangements. We're not going to cover all of those. We're pretty much probably only going to talk about cycloadditions. The other ones typically get covered in a graduate level organic chemistry course. So let's look at some more examples of this reaction so you can get comfortable with sketching the products because they can get pretty exotic and they can get pretty complex pretty fast. So again, you just have a diene, you have a dienophile, an alkene. Doesn't matter what's attached to the alkene. It's just along for the ride. So again, we're going to take those electrons there, these here, those there, make a 6-member ring. Double bond there, and then we still have this aldehyde attached there. Right? So we took 2 pretty simple molecules and made a much more complex molecule in one reaction. Or if we take these 2 molecules, so the CN groups are just along for the ride. So these electrons go there, those 2 there, these 2 here. And you make that. And then, so what is significant about this reaction is that cycloaddition reactions are stereospecific. So these 2 groups started cis, and so they will end up cis. Right, either both up or both down. Of course, it doesn't matter in this case because that's a meso compound, so both up and both down will be the same molecule. Or if they're trans, like in this case, they start trans, so they'll end up trans. So here your diene is more complex. So the oxygen is it's not participating, right? So but these electrons go there, those electrons go there, these electrons go there. So it's, again, it's always the diene, and whatever's attached to the diene is just tagging along. and then it's always the alkene, and whatever's attached to the alkene is just tagging along. So that would make so you've made a bond between these two carbons, right? And then this has to stay trans to each other. So you would make that, right? Or you may see this drawn like this. Right, same molecule, just a little bit more exotic drawing of it. But the point is, I don't care how you draw it, you just got to get the bonds in the right spot. So again, you always make the bonds between the ends of the pi system. So bonds between those two carbons and bonds between those two carbons. And then you have to recognize the double bond's going to flip to between the diene. So you can also use alkynes. So just one of the pi bonds. So it goes here, those two go there, and these two go there. And you would make. So there's still a double bond left between those two carbons then. You would make that, right? Or more customarily drawn like. Like that. Okay, so this example just to show you kind of how exotic they can get, or how much more complicated they can get. But if you recognize here, you have a diene, and you have an alkene. You have a dienophile. So you have everything that you need to do a Diels Alder reaction. So let's take this and draw it a little bit differently to make this easier to see. Okay, so let's see, 1, 2, 3. So that's the same molecule, right? But now we've aligned up the alkene with the diene. Okay, so this goes there, that goes there, this goes here. So we're going to make a ring. And again, anytime you make a ring in organic chemistry, it can be useful to number that ring. So let's call that 1, 2, 3, 4, 5, 6. So we're going to have two 6-membered rings fused to each other. And we have called this carbon number 2, and we've called that carbon number 3, and that's 1 and 4. So this is 5 and 6. So now get everything attached where it's supposed to be at. So between 2 and 3, there will be a double bond. So let's see. 4. So between 4 and 5, there's, we'll call this atom 7, 8, and 9. So between carbons 4 and 5, there's atoms 7, 8, and 9. 7, 8, and 9. 7, 8, and 9. And so carbon number 9 is a C double bond O. Right, so that would be the structure of your product. Okay, so now the theory of the Diels Alder reaction. So this is also what's called a 4+2 cycloaddition reaction. So first of all, this diene, so for the Diels Alder reaction to work, so this is S trans, right? For the Diels Alder reaction to work, it must adopt a cis conformation. So this is S cis. And now it's set up to do the Diels Alder reaction. Okay, so second, we need to explain the theory. To explain the theory, we have to look at the molecular orbital map, the molecular orbital picture. So we did this in the third lecture from this chapter. So you would definitely want to go through the third lecture before you look at this lecture, otherwise this won't make any sense to you. Okay, so in the third lecture we looked at the molecular orbitals for diene. So if you remember, pi 1, pi 2, pi 3, pi 4. So pi 2 was the highest occupied molecular orbital, and pi 3 was the lowest unoccupied molecular orbital. And for the alkene, so the dienophile, so there's only 2 carbons with a p orbital, so they're either in phase or out of phase, and there's 2 electrons, so this is the highest occupied molecular orbital is pi 1, and pi 2 is the lowest unoccupied molecular orbital. Well, so for the Diels Alder reaction to work, so you have to take the highest occupied molecular orbital of the diene. So this has to interact with the lowest unoccupied molecular orbital of the dienophile. So we need to take those 2 molecular orbitals. So I've resketched them here. So the highest occupied molecular orbital of the diene and the lowest unoccupied of the dienophile. And when these react, they react top to bottom. So they approach each other top to bottom. Either diene on top and dienophile on bottom, or dienophile on top and diene on bottom. And then what you want to do is look at the ends of the pi system. So the ends of the pi system have to both match, meaning they're both in phase. So if both ends match, if they're both in phase, the reaction works. That's the theory. The theory predicts that this reaction will work. So, you know, in reality, the theory is more complex than that, but that's the basics of the theory, and it's enough to explain what we're going to talk about in this class. But those who figured out this theory and a way to explain these reactions using this, they won a Nobel Prize in 1981 for their work. So this analysis is what's known as Fmo Theory, or frontier molecular orbital theory. So this explains why the 2 + 2 cycle addition does not work with heat, but it does work with light. So if you just took 2 alkenes and you heated it up, can this happen? Can you just move those electrons like that and make cyclobutane? Well, the answer is no. Not if you heat it, but if you shine light on it, then it works. Then you can make a cyclobutane. So how does that work? So again, to understand that, we need to look at the molecular orbitals. So we have 2 alkenes, so the molecular orbitals look the same, right? We have the highest occupied molecular orbital, pi 1, and pi 2 for both. So we need to take the highest occupied molecular orbital for one and the lowest unoccupied molecular orbital for the other. Okay, so this would be the highest occupied molecular orbital for one, and this would be the lowest unoccupied molecular orbital for the other. And if we let them approach each other top to bottom, then you can see these 2 match. They're both in the same phase, but these 2 don't match. They're out of phase. So there's no constructive interference overall, so that reaction would not be predicted to work. All right, so again, we have a match here, but we have a mismatch here. Or this is bonding, and this is anti-bonding. So there's no net bonding. So theory predicts reaction. So the theory predicts the reaction does not work. Right, but if we go back to this one, where we had a match and a match, so this is bonding, and this is bonding. So they're both are bonding, so that would be 2 constructive interference. That would be, theory would predict that that reaction should work. Doesn't mean it's going to work in high yield, it just means it's predicted to work. Okay, so if we go back to this with the 2 alkenes, so if they react with each other, it does work if you shine light on it. So why? So what happens if you shine light on it? Then if you remember from the 3rd lecture, that promotes an electron from pi to pi star. So this is pi. This is pi star. So now we have 1 electron in each of those orbitals. So now what we need to do is we need to take the lowest unoccupied of the ground state, and we need to take the highest occupied of an excited state molecule. So we need to take one alkene that looks like this, that has not had light shined on it, and we need to take one alkene that looks like this, that has had light shined on it. So if you take this reaction mixture and shine light on it, not every single molecule in that reaction absorbs light. Most of them don't. So only very few of them are in the excited state. Most of the molecules are still in the ground state. So if we take the lowest unoccupied for the ground state, right, so that would be taking this orbital, and we take the highest occupied of the excited state, so that would be taking this orbital for a different molecule. And then now we can see that there's a match and a match, so that's bonding. That's bonding. Both ends of the pi systems have bonding interactions, so the theory would predict that this reaction works. How many electrons are involved? There's only one electron, right? Because this would be the highest occupied of the excited state ethylene. It has one electron, and this would be the lowest unoccupied of the ground state ethylene. It doesn't have any electrons, but one electron is sufficient to make the two bonds. So the reaction is predicted to work in the presence of light, but does not work in the presence of heat. So basically, systems that have 4n plus 2 pi electrons require heat in order for them to work. So to be allowed according to the theory, and systems with 4n electrons, with 4n pi electrons require light to work, or to be allowed according to the theory to work. So how did we count electrons? So this will be what's called a 4 plus 2 cycle addition. So we got 2 electrons there, 2 electrons there, 2 electrons there, so we got 6 electrons total. So 4n plus 2 equals 6, 4n equals 4, n equals 1. So if 4n equals 6, so if we took a 4n plus 2 and a 4n and let them both equal 6, which one equals an integer? Well, the 4n plus 2 equals an integer, so this is a 4n plus 2 system, so this requires heat for this reaction to work. And you would make the cyclohexene. If you did this reaction, there's 2 electrons here and 2 there. So if we did 4m plus 2, so there's 4 electrons total, equals 4. So it does not fit a 4n plus 2 system, because n does not solve for an integer, it solves for a fraction. If you set it equal to a 4n, so 4n equals 4, n equals 1, it fits a 4n system because n solves to an integer. So that requires light. So you shine light on this, and it does a 2 plus 2 cyclo addition. And this would be a 4 plus 2 cyclo addition. Okay, so are they 4n plus 2 or are they 4n systems? So those electrons go there, those go there, those go there. So again, this would be a 4 plus 2, 6 electrons, so that's a 4n plus 2 system. So this requires heat. What would that look like? Product would look like that, right? Because these two groups, 2 C double bond doughs, started cis to each other, so they got to end up cis to each other in the product. And this one, again, since we're only using 2 of those electrons in the triple bond, This is another 4 plus 2, 6 electrons, so it's a 4 and plus 2 system, so it requires heat. And you would make that. If you did this one, so those go there, those go there, those go there, these go here, and you would make this 1,3-cyclooctatetraene. How many electrons is that? Well, this is 6 electrons plus 2, that's 8 electrons. 8 electrons fits a 4N system. So this reaction requires light to work. And this one, so if those go there, those there, those there, those there, then that's a 4 plus 4 is 8 electrons. So this is a 4N system. So this reaction would require light as well to work. So what if you used heat instead? So if you use heat, it can't do a 4 plus 4, but it could still do a 4 plus 2, where only one of these reacts. Which will give you that. That's the major product instead. Okay, so again, so whether a cycloaddition reaction works or not depends on whether you have light or heat. And the product that you get out, if the molecule has options, will depend on whether you use light or heat. So it's pretty complex, right? And the theory is pretty complex. But for the theory, you have to know what the molecular orbitals look like. And you have to take the highest occupied molecular orbital of one and the lowest unoccupied molecular orbital of the other molecule, and then see if the two ends match, if they're both in phase or not. If they're not in phase with heat, they will be in phase with light because you promote an electron, and that switches what would be the LUMO. Okay, so hopefully that makes sense.